Hello and welcome to Chapter 4. In today's lecture, we are going to go over um, the physical layer and the data link layer of the OSI model. So let me just go back to the very beginning of the chapter. Um, so our objective is really to understand how a NIC operates, which is at the data link layer and the physical layer of the OSI model, and what actually happens. All right, so let's start with, let's say you want to connect, let's say you have a home router at home. Um, your internet IP address, your internet connection goes from here to the cable modem, and your router, your wireless router, this is your wireless router at home. The antennas are embedded inside the box itself. We'll get an IP address directly from the cable modem, and then you can access your devices there without wirelessly, or you can use any of these 4 ports. This is actually a switch embedded within your router. So it's preferable that you use the switches because you get much better speed and there's not a lot of interference with your signal. Okay. All right. Now, if you can connect, like I said, wirelessly. So if you are close enough, again, it's preferable that you do that. It's much better. You get a much stronger signal and you got um, more reliable connection. Let's put it that way. Even though your wireless routers now offer you, in some cases, better speed than the wired connection if you wanted to. All right. For example, let's say your wireless router right here in the corner, and let's say your smart TV. You want to connect your smart TV to your wireless router, but the signal is very weak. And if you're watching Netflix, you may get interrupted every once in a while. You're watching a streaming video. So what you could do is you can get yourself an extender. The extender will receive the signal from the wireless router and boost the signal so you can have a better connection. Well, this might cost you a little, $30 to $40. But if you can run a wire from your wireless router to your smart TV, because it does have an Ethernet port, that would be the best way to go. Because then you have direct connection. And if you're running, let's say 100 megabits per second, you can almost watch anything in HD streaming video. All right. So that could go, goes directly to your any outlet at home. All right. The physical layer. The physical. If you remember when we talked about the encapsulation and decapsulation process, so you got the source where you got your applications and they get encapsulated as it goes down. It goes into segments, packets, then the packets gets encapsulated into the frames and the frames are placed on the wire in ones and zeros. Now on the other end, the receiver will receive these ones and zeros, pick up the frame, that's your NIC will do that, and then the frame is opened up. You grab the packet, pull the packet out, then you grab the segment out of the packet, and then the application, according to the port number, will take the data out. Here, let's review this one more time. So here's some notes I've written out. It's probably a good idea for you to write them down. Here are the 7 layers of the OSI model. If you remember the protocols up here, depending on which protocol you're going to do, the PDU, protocol data unit, called at the top layer, um, is called data. We really take the presentation, the session, all these top 3 layers. SMT, for example, covers the layers of 7, 5, and 6. In our CCNA program, not W203, 5, 7, and 9, we really don't discuss much of the presentation in the session layer. But all of these protocols are embedded within them. But for example, presentation is how you present the data. Talk about how, what format, for example, the picture should look like. The MPEGs, MPEG 1, MPEG 2, MPEG 3, MPEG 4, the way you compress videos, or the MP layer 1, 2, and 3 for voice, for example. That all goes at the presentation layer. The session layers are something like, the SIP, the Session Initiation Protocol, is the one that sets up the session between two voice over IP packets. But anyway, that will be discussed maybe in another course, but not. It's beyond the scope of this. What we're really doing right here. So again, you take that data, ones and zeros, you give it to either to TCP or UDP. What does the TCP and UDP do when it receives the data? It's going to break up the data into smaller segments. And then on each segment, you put a port number to identify which application is going to be in those segments. By the way, sometimes UDP, when it breaks up the data, we call them datagrams sometimes. We don't call them segments, but most books calls everything segments up here, the pieces of data that has been broken up. So port numbers are stamped on those segments to identify what application is being used. Then these segments are given to the IP protocol at layer 3, and the IP protocol places those segments into packets, and on the packets you place the IP addresses, the source IP and the destination IP address. Remember, the source IP is given to you from your DHCP server normally, and your destination IP address is given normally from your DNS server, because you type in a name, your computer goes out and looks for an IP address for the name that you gave it, like www.devry.edu or www.microsoft.com or whatever. Then those packets are given pretty much to your NIC, either an Ethernet or a wireless 802.11 NICs. And what the NICs do is they encapsulate those packets into frames, and they put their MAC addresses on the frame. What is the MAC address? Communicates between two devices that are directly to each other. You receive your MAC address from your NIC. There's a MAC address that is burnt on a ROM chip on the NIC. So that's where you get your MAC address. To get the destination MAC address, you send out an ARP request requesting it. If you remember, we discussed that in chapter 3. So after you send out an ARP request, you say, whoever has this IP address, please give me your MAC. And then somebody will, in your LAN, will respond, either a host in your LAN, and if nobody responds, then you're going to do an ARP request for your default gateway, and then that means your packet will go outside. Now, once you got the frame ready to go, then it's placed on the wires at the physical layer, bit by bit. All right, so question number 1, please write this table down. All right, so that's one of the questions that you will have to answer. I want you to write it down. Just replicate this table. All right, let's go back and continue with our slides and see what is the slides got to say. Okay, so there's your physical layer at the bottom where your signals are actually traveling. Here's some typical, if you ever probed the wires, you will see a signal like this to indicate that this is for example, this is going up as a 1, down as a 0, up as a 1. This is a typical signal on an unshielded twisted pair cable. This is the typical signal that you would see on a fiber optic cable. The darker red color is a 1, the lighter the color is a 0. When you go wirelessly, data has to be modulated, converted from ones and zeros like this into an electromagnetic wave analog signal. So this is an amplitude modulation, means to make an analog signal look like this 0, give a small amplitude, low amplitude. High amplitude means a 1. You may use frequency modulation, where low frequency is a 1, high frequency is a 0. Or you can do phase modulation. You don't touch the frequency or the amplitude. The amplitude will be, as long as you are going up and down, that's 1, a 0. Then as soon as, this signal is supposed to go up, but now you flipped 180 degrees and you started going down again, up. Once you change the phase, That's what phase modulation means. Then you switch from whatever bit you were sending to the opposite. In this case, from a 0 to a 1. All right. All data, digital data that is being transmitted in the air must be modulated. Modulation means converting the digital data from ones and zeros to an analog signal. And demodulation is grabbing these analog signals from the air, electromagnetic waves, and converting them back into ones and zeros. Okay? That's what really a modem stands for. MO for modulation, DEM and modem is for demodulation. All right. AM signals are typically susceptible to noise because the noise out in the air will change the amplitude of the signal. But FM, as you can see, we're not concerned with the amplitude, so it's less susceptible to noise. That's why FM radios, for example, have less noise in them, and you can actually send more data. Anyway, here are some physical standard organizations that we also discussed in Chapter 3. The International Organization for Standardization, those are the ones that came up with the OSI model. The EIA-TIA, this group is really looks at all the standards for cables, coax cables, the copper cables, the pins that are in there. The American National Standard Institute, together with the EIA-TIA, looks at the register jack 45 pinout, the RJ45 connector that goes onto our patch cables. The International Telecommunication Union telecommunications sector is really, this is the worldwide organization for telecommunications that we discussed last week. ISO are part of the, they came out of the ITU, but now they're a completely separate organization. The IEEE is the ones that house all the LAN and MAN protocols, such as the 802.3 Ethernet, the wireless 802.11, Bluetooth 802.15, WiMAX 802.16, Token Ring 802.5, and so on. All right, the physical layer. You have typically copper wires that are out there. Those are the most common. You have fiber optic cables, or wireless. Fiber optic, more for corporate environment when you have a, when you wire your whole building in fiber, and it could be hospitals, for example, banks needs to connect. They need data to be transferred as quickly as possible, or you need, for example, in hospital, you need to transfer images with very high resolutions, and you want to make sure that there is no interference, and you always want to have connection. So fiber is really the preferable if you got the money for it, of course. Copper wire is the most common because it's the least expensive, and most buildings are already wired with Category 5 enhanced wires that can support up to a gigabit Ethernet. Okay, the data, depending on what type of NIC you have, the data gets encoded on the wires in many different ways. For example, the Manchester encoding is used by 10-base TNIC. 4B, 5B codes are used by 100-base TNIC. The gigabit Ethernet uses the 8B, 10B NICs. And what you look for is the changes in the electromagnetic field intensity to either determine if it's a 1 or a 0. Okay? When it comes to fiber optic cable, it's really pulses of light that you are sending inside that fiber. If you have a light, it's a 1 if you're trying to detect it, and it's a 0 if there is no light. When it comes to the wireless media, you have two ways of encoding the data, which really modulating the data, either using the direct sequence spectrum, which really means taking the actual data that you're trying to transmit and spreading it over a bigger signal, or use the orthogonal frequency division multiplexing, which really you spread the signal out and you pick the strongest signal to be transmitted. OFDM is the best way to do it for wireless because it it um, it modulates and demodulates the signal very quickly. So you expect um, 802.4 N, for example, 802.11 N, for example, uses OFDM to modulate and demodulate the signals going out. So this is a copper wire, the unshielded twisted pair cable. This is a fiber where the data could be transmitted in light waves. And this is wireless where the data is in electromagnetic wave. All right. A couple of things now you need to know. You need to be able to differentiate from now on the difference between the word bandwidth and throughput. The word bandwidth means maximum speed limit, and it's measured in bits per second. The word throughput is the actual speed. For example, let's say you are on some route, some highway, and the highway speed limit is 65 miles an hour. So that 65 miles an hour is the maximum speed that you can be traveling on. So that's what bandwidth is. You can't go any faster than 65 miles an hour. On the other hand, throughput is the actual speed. So for example, if you are going 40 miles an hour, so that's your throughput. Why are you going 40 miles an hour on a 65 mile an hour highway? That's because there's traffic, right? Could be anything. All right, so speed again is measured in kilobits per second. Megabits means a million. Giga means a billion. And tera means trillion, right? So throughput means the actual speed. So now that's the difference. So when somebody says I got a bandwidth of 100 megabits per second, that's not necessarily, they're not going to be getting 100 megabits per second all the time. It all depends on the actual speed that you are uploading or downloading is what throughput is. All right, so if you take a look at the back of the router, this is where the physical connection to the router will be, the wires. For example, right here is where you connect your default gateways. There are two LANs that you can connect to. All right, so these are actual NICs, just like the NICs that you have inside your PC. Two USB connector you can connect to the router. This is if you want to get in and manage with using the console port. If you connect the console port to a serial port on your PC, or you connect the auxiliary port to a modem that you have on your PC. The auxiliary port is hardly ever used. We always use the console port. You have a mini connector right here. You can a mini USB connector if you need it. Uh, a synchronous high density DSL connection. This router has, and it has a switch, 4 switch ports. Actually, there's a little bit more right here. All right. So those are connections in the back of the router that you can use. Okay, let's get into the network media, the cables. Here's a typical signal that you are transmitting. Now, if this signal is being transmitted on the wire and the wire wasn't designed that great, there may be some interference. And here's an interference signal that will add, like I said, to the amplitude and change the amplitude. So here's the digital signal with interference traveling on the wire. And on the other end, this is what you're going to see. So the computer is going to have a hard time interpreting ones and zeros, right? So you want to reduce the interference signals as much as you can, or filter that signal out so you get a nice clean signal on the other end. That's the reason we limit the distance to how far data can go. Not only that the signal will weaken, attenuates, but also interference signal. And the farther you send the signal, uh, the greater the interference signal will detriment your the way the way you will actually receive the signal. So we'll make the distance a little bit shorter, so you can interpret what the original signal was. All right, so here's some copper wires. We have the unshielded twisted pair cables. There are 4 pairs. Each pair has 2 wires, of course, and they are twisted. We'll talk about the twisting and why we are twisting it in a few minutes. You have They are unshielded from outside electromagnetic interference. Here's a shielded twisted pair cable, and this shield is to protect it from the outside of electromagnetic interference. Here's a typical coax cable. This is a copper wire, and this is some waxy material, everything. And this is a braided copper wire. This is really, as we will discuss also later on, is to keep the electromagnetic wave that is traveling inside here to be bounded. So that's really what a coax signal is for. All right, the unshielded twisted pair cable. Just a couple of things we need to go over before we understand what the unshielded twisted pair cable and how it works. When you conduct electricity, conduction of electricity means, or current flowing in the wire means that there are electrons that are moving inside a copper wire. How do these electrons move? These electrons move is by a force caused by a magnet. So when you put a magnet next to a wire, that will cause the free electrons in a copper wire to move. When these electrons move, they emit energy, and that energy is what electricity is. You use that electricity to you use that energy to light a light bulb or power your PC or whatever. But they also emit the same magnetic force that was applying on them. So if you put another wire a wire that's not conducting electricity next to another wire that has current flow in it, the wire that does not have electricity in it will conduct electricity because of the magnetic force that's being emitted by the live wire. So that's why we're trying to keep the wires away from each other. Now, the good thing is if the current is going north and there's another wire next to it, it has current coming south, the magnetic force that's emitted by each of the 2 wires cancel themselves out because they're going opposite direction. So that is the reason we twist the wires. We twist the wires so they can change direction, and therefore the electromagnetic interference that's caused by one wire will be canceled out from the other wire. So therefore there's not a lot of interference. The more twists you have, um, the more um, the more protected it will be. Well, the longer the distance can be. So we're really not concerned with the twists. You are going to go out and buy them, and they are going to be set with the twists and everything that you need. So again, why do we twist the wires in an unshielded twisted pair cables? To make sure we cancel the magnetic interference that's caused by the wires themselves. Now, but they are not protected from outside electromagnetic interference. So therefore, you do not want to place your unshielded twisted pair cable next to any devices that emit electromagnetism, such as big power um, tool drives, electrical tools, for example, power tools, big machineries that has a lot of electromagnetism next to them, even fluorescent light. So if you have to run your wires, you know, above the ceiling and there's some fluorescent lights, you're trying to keep them away from there because they will interfere with the signals, even though they're just emitting a very small amount of electromagnetism. Okay, so, but there are really, most buildings don't have a lot of electromagnetic interference. So that's why they use unshielded twisted pair cables. It's the least expensive way that you could do this. Okay, so we'll get into the color codes of the unshielded twisted pair cable later on. All right, so question number 2. Why do we twist the wires in an unshielded twisted pair cable? And the reason is to cancel out the electromagnetic interference. All right, you may use a shielded twisted pair cable, put a braided foil right here on top, as you can see, and that will protect it somewhat from the outside interference. But that causes a little bit of a problem between the braided signal and the inside, the signal that's being emitted outwards, and that reduces really the distance for shielded twisted pair cable, and it's a little bit more expensive. Um, Very few networks require a shielded twisted pair cable because of the money that you have to spend on getting a shielded twisted pair cable. It's preferable that you use fiber. I think Cat 7 is using a shielded twisted pair cable to achieve the 10 gigabit Ethernet that it can support. All right, now let's look at the coaxial cable. Coaxial means the CO in coax mean common, AX, axes. What's common axes? It's this copper wire and this braided copper wire on the same axes, right? Now, when you run current in this wire, an electromagnetic wave will be emitted in this waxy material outward. This braided copper wire is meant to keep this electromagnetic wave that's being emitted bounded inside, and the electromagnetic wave travels this way. So the coax cable is mainly used to bound wireless signals, really. Okay, and it's mostly used nowadays for videos. It used to be used in networking in TIM-based 2 and TIM-based 5 networks, but that's no longer really. Those are legacy Ethernet, and we no longer use them for net because they're pretty. They can some of them can support up to 100 megabits per second, can give you 500 meters in distance, which is not bad, but it's very difficult to work with. And again, we need a lot more bandwidth nowadays than 100 megabits per second. Okay, you can use the F-type or the B and C connectors. Typically are seen when you connect them to the TVs. Make sure that the connectors are nice and tight, because otherwise you'll lose the signal going out. If you go out to Home Depot or any place that you want to buy a cable for your TV, look for RG6. RG6 is really designed for video, and the way it's designed, that will give you the best signal. All right, copper media safety. All right, because electrons are flowing inside the wire, they need to keep flowing. So either you continue the circuit, or if there's no continuation of circuit, make sure that all wires are grounded, so that any wire that does not have a ground may cause a problem. So, that's one of the reasons you have a big pole outside your home, metal pole, to make sure all the electricity is grounded. So in case if there's any problems, everything goes into the ground, and you don't harm your devices. Okay, so everything has to be grounded, and you check for that. You don't have to worry about that if you're having, by the way, fiber optic wiring, because fiber optic uses light, and light has nothing to do with electromagnetism or current or anything like that. So it's immune from all of these problems that we have. All right. So again, we use the unshielded twisted pair cable. We use the unshielded twisted pair cable mostly in the corporate environment because they are the least expensive. Okay, and we twist the wires to cancel out the electromagnetic interference, the EMI. Sometimes they call that noise, crosstalk. Let me get all of that. All right, there are 7 categories of the unshielded twisted pair cables, from Cat 1 to Cat 5. Cat 5, I'm sorry, to Cat 7. Cat 7 is the latest and the greatest, and it can support the 10 gigabit Ethernet. Cat5 Enhanced supports 1,000 megabits per second on a copper wire, and most buildings are, and these are the least expensive too. So that's why a lot of people will go for that. They don't have to change the wiring. All they got to do is change their NICs to gigabit Ethernet, and they're good to go. Yeah, unfortunately, the switches are expensive. Connecting all these gigabit Ethernet NICs onto a switch, a port can cost you up to $100 a port. So that's one of the reasons a lot of companies, especially when you have a lot of hosts, they don't want to go for the gigabit Ethernet. They stick with the um, the fast Ethernet, which is the 100 base T NICs, 100 megabits, because of the switches. The switches are expensive, but hopefully the prices will drop. All right, here's your RJ45 connectors, the register jack. If you're wondering what the 4 and 5 means, it's really for the ring and tip. If you ever had voice, there are two pins that for the ring and tip when you use it to make phone calls. We don't have to worry about that. That's just good to know, not need to know. So there's your RJ45 connector, and the unshielded twisted pair cable goes in there. If you ever need to make one, make sure that the jacket goes all the way inside, and these are nice and tight. Do not unwind the wires a lot because you get what's called near end when you do that, right? Here's the sockets that you have to do, and on the other side of the socket, this is where you put, you match the color and you punch the wires in there when you are connecting them. Very easy, not a lot of things you need about when you are really making an RJ45 connector. All right, there are two really standards, the 568A and a 568B, and it's highly recommended that you remember the color codes from left to right. So when you are making, this is the RJ45 connector, so make sure that the tip is down. Pin 1 is on the left, pin 8 is on the wire. There are three different types of cable that you can make. The straight through, the crossover, all over. We'll get back to that in a second. So for example, remember, here's one thing to remember. Ethernet 10 base T and 100 base T NICs, they transmit at pins 1 and 2, and they receive at pins 3 and 6. Question number 3. What pins do Ethernet transmit and receive at? Well, the Ethernet base 10 and 100 base T. Ethernet 10 and 100 base T NIC, they transmit at pins 1 and 2 and receive at pins 3 and 6. Okay? And as you can see, for example, if you go in and let's say somebody told you, I want a straight through cable, that means pin 1 has to match pin 1 on the other end. So you just let, for example, follow 568A on one end and also 568A on the other end. And that will give you a straight through cable. Pin 1 to pin 1, pin 2 to pin 2, pin 3 to pin 3. If you wanted to do a crossover cable, that means pin 1 has to match pin 3 on the other end. So you do 568A on one end and 568B on the other end. Now, as you can see, pin 1 will be, the transmitter of one side. Pin 1 will be connected to pin 3. See, it's striped green, and then pin 3 on the other end is striped green. Pin 2, solid green. Pin 6, solid green on the other end. Okay, 3, striped orange. And where's the stripe orange now? Right here, pin 1. So 3 to 1 and then 6 to 2. So if somebody says, I want to cross over a cable, so you go on one end, follow the 568A standard, and on the other end, you follow the 568B standard. If you wanted a straight through, you just make sure that the same standard is on both ends. Okay? Here, I wrote that also on some of my notes. Let me just go back in here. So here's some of the notes. Straight through cable, pin 1 to pin 1, pin 2 to pin 2. Crossover cable 1 to 3, 2 to 6, 3 to 1, and 6 to 2 on the other end. But pins 4 and 5, 7 and 8 are not really used. When do you use a crossover cable? When you want to connect two like devices together. For example, you want to connect a PC NIC to another PC NIC. Because if you use the straight through cable, pin 1 is going to be sending the data to pin 3 of the to pin 1 of the other PC, and that's not good. So you use a straight crossover cable so you can send data from pin 1 to pin 3 directly, right? So crossover cable is when you want to connect PC to PC, router to router, switch, for example, like devices. Use a straight through cable when you want to go to a hub or to a switch, a PC to a hub or to a switch, because the switch or the hub itself will take pins 1 and 2 that you're transmitting at and send them to pins 3 and 6 to the receiver. That's where the switching happens. The rollover cable, by the way, if you want to construct a rollover cable, pin 1 to pin 8, 2 to 7, 3 to 6, it's a complete crossing over the rollover. And the rollover cable, you use that whenever you want. It's a Cisco proprietary cable, which means you only use the rollover cable to connect to a Cisco router or a Cisco switch. All right. Those are the blue cables that we could use last week to connect to the router so we can manage it. All right. Lots of time you may work in a place where you have to test the unshielded twisted pair cable using a fluke device. So you can send a signal out, check the wire map. For example, if you want to see where there's any discontinuity in the wiring, you can check out the length of the cable. You can check out to see how fast the signal attenuates, loses its amplitude. So you may need to use a repeater, or maybe there is some massive interference that's causing the signal to degrade rapidly. And you can look for noise, electromagnetic interference. And, this is for troubleshooting purposes. Fios now, they have fiber right into your home. So everything goes into your home, and inside your home, obviously, you probably might be using cable, coax, but that's what Fios is really doing. It brings everything into your home now from outside. By the way, cable TV does that too. The only thing is it goes from outside your home. There, let's say it's on a pole. From outside, from that switch to your home, into your home, they use a coax. But that connection on those wires coming into your neighborhood, that's all fiber as well. All right, so let's talk about the fiber optic cable. Fiber optic media, the fiber is really a small piece of plastic, you can think of it, or glass. And light travels in very, very fast. Light travels at 300 million meters per second. A light signal can travel around the Earth 7 times in 1 second. That's how fast light travels. Now, when it travels inside a cable, a fiber optic cable, it goes pretty much at the same speed. Now, this core can be as small as the diameter of the core of the fiber. They can go up to 5 micron, 5 over 1/1,000,000th of a meter. The width of your hair is 200 microns. So that means this fiber is 40 times smaller than the width of your hair. You can't see it. And it can handle gigabit of data, 100 gigabits of data, in fact. Now, when you shoot the light, to make sure that the inside the core, you want to make sure that light, the intensity of the light, because that's what's going to determine a one, stays light and doesn't lose any of its energy as it travels. To make sure you put cladding around it. So cladding goes around the fiber to make sure that the light signal stays bounded and it doesn't lose a lot of its energy. The rest of the stuff that you put on there is just to, you buffer it. You use a buffer in there, and then you use strengthening material to make sure that the fiber doesn't, get, breaks up, and then you put a jacket on top of it. Otherwise, you won't be able to even to see it. And by the way, full fiber optics are always full duplex, as we will discuss later on. You're always transmitting and repeating. There are two different types of fiber media. There's single mode and multi-mode. Single mode means you're to transmit one signal. So if you're trying to transmit one signal, that signal is going to take one path. And it's best to send that signal right in the middle of the core. Why? Because you don't want it to bounce up and down, because if it bounces, it will lose its energy. And if it loses energy, then it's not going to travel as far. Single because of the distance that it can cover up to 100, 10 kilometers or even more before it needs to be repeated. Um, it used for voice a lot. It can be used for data. It has a small core. It uses lasers as the transmitters. And it's not too bad, but when you want to get high bandwidth, you want to use the multi-mode. That means you have to send multiple signals. And if you send multiple signals, it's best to have each signal take a different path. So you need them to bounce off the inside of the core. And therefore, you expect the distance for a multi-mode fiber to be a little bit shorter than the single mode. The core is a little bit thicker than the single mode, and they use LEDs, the light emitting diode, as the light source. When the light goes up, that's a 1. When it dies, that's a 0. So if you're talking about gigabit Ethernet, an LED can go on and off a billion times just for gigabit Ethernet. And signal gets dispersed more with multi-mode. Dispersion means if you are very far away and you're trying to detect the signal, you cannot differentiate between a 1 and a 0. All you see is light. You can't see on, off, light, on, line, off. After a certain amount of distance, the light gets dispersed and all you see is ones. That means the signal has dispersed. So there are ways of getting around that, but it's very difficult. All right, so question number 4. Let me just go back. I want to ask a question on that. List the characteristics for single mode and multi-mode, and there they are right here. All right, so copy these down for single mode and multi-mode. Let's continue. Here are some typical fiber optic connectors. You got the straight tip connectors, the subscriber connectors, the loosened connectors, and the duplex mode connectors. I remember when I did my CCNA, I had these pictures on the test, and they were asking me what kind of cable connects to these connectors. Obviously, it's a fiber. All right, you may have the OTDR, the optical time domain reflector. This is the tester for fiber optic cables. These devices are very, very expensive, by the way. They can go up north of thousands of dollars. All right, and here is the comparison between a fiber and a copper wire. Obviously, when it comes to a choice, of course, you want to go with fiber because it gives you higher bandwidth, distance. You can go up to 100 kilometers, immune from electromagnetic interference. So because that means you can put it next to machineries that emit electromagnetic interference and it will have no effect. The media is expensive though. High bandwidth, long distance, immune from EMI. But on the other hand, it costs a lot of money. You need people with skills to install it and troubleshoot it and maintain it. And if there's any problems, the equipment to splice, put the cables back together are expensive too. So it's not cheap. But you get the best bandwidth, and for the future, that's probably what you need. And that's the idea behind Fios when they actually started rolling out fiber into your homes, because the idea was down the road, everybody is going to need very high bandwidth, and they're already going to have the wires coming into your home, so they'll be ready to go regardless. All right. Now, the wireless media. The wireless media really mainly uses the ISM band, the Industry Medical Band. The FCC, the Federal Communication Commission, has reserved a block of the spectrum for frequency that you can use privately without having to be regulated or licensed. And that ISM band, with not a lot of power, you can't use it to transmit with high power, of course. They're limited power. The 2.4 gigahertz, the 5 gigahertz, now they have the 9 gigahertz, the old 900 megahertz, all that is within the ISM band. And so that means all of our devices that we use at home, from the microwave to the cordless phone to our wireless LANs, are all within the ISM band. Now, they don't have a lot of power, so the signal doesn't radiate very, very far. So the coverage area is not that, is only maybe within 100 feet, 150 feet or so, 300 feet now, maybe a little more. There's a lot of interference, of course. Anything metals interferes with the signals. Thick walls interferes with the signals, and so on. The best way to place your router at home is to put it in an area where there's not a lot of obstacles around. If you can put it right in the middle of the house on the ceiling, that would be great. And if you have antennas, you want to point these antennas towards the devices. Security will always be an issue because your signal is emitted outward. Even though you can encrypt the data, somebody can jam your signal. That's called denial of service. All right, so other than Wi-Fi, you have the Bluetooth, where you have two devices that want to communicate directly to each other. So you can achieve up to 3 megabits per second with Bluetooth devices. Now, Bluetooth devices don't use a lot of power, so you can use them in small devices, the one for the earpiece for your phone, remote controls, and phones can send data to each other. But now they have something called the NFC, the near field communications, where if you bring your devices very close to each other, they can transfer even more data. Apple just recently using the Apple Pay, they're using the NFC connection where you can put all your credit cards on your PC, on your phone, and it'll be encrypted, and you just scan it, and you have to really carry credit cards anymore. You can use your airline e-tickets using the same idea. WiMAX is really an idea that was supposedly to give you broadband connection. They compete with cable TV and FiOS. They want to be able to give you data, voice, and video with a 6.5 mile radius. Um, you have to have an antenna. So that means you can go out within 6.5 mile radius in a metropolitan area, city limit, and have your voice, data, and video always with you and be connected. And you can get up to gigabit connection. I don't know, it didn't kick in as they were hoping for. They envisioned that everyone will have a wireless LAN, and the WiMAX will connect all of these wireless LANs together, and eventually they'll be connected to the internet. So that might be coming soon. How fast it's going to grow, we'll see. Here's a typical wireless LAN, the latest and the greatest from Cisco, the 11AC wireless router. Of course, the antenna is embedded inside the box, which you don't see. And here are the standards for the 802.11. AC's already been out. I'm not sure about the AD. But look at the AD. It can give you a maximum speed of 7 gigabit per second. That's pretty good. That's pretty close to the 10 gigabit wired Ethernet. And it's backward compatible to BG and then AC. AC is already out. A lot of devices support AC, 1.3 gigabit. This is only going to your wireless router, of course. It's not too bad either. right? And this distance is not is great. So wireless is here to stay, and and that field is growing fast. All right, now let's get to the data link layer. We just finished with the physical layer, and now you have an idea about all the different wiring and signals that at the physical layer. All right, let's get to the data link. The data link layer, which is layer 2 of the OSI model, is composed of two sublayers. The LLC, the logical link control sublayer, that's the one that communicates with the network layer. That's the one that grabs the packet from the network layer. And the media access control sublayer, that's the one that takes the data from the LLC and with the frame and places the frame onto the physical layer, the wires. That's media access control. Your NIC actually operates at the max-up layer and the physical layer, the standards of your NIC, such as the 802.3, the Wi-Fi, all these NICs. All right, so if somebody asked you, where do the NICs operate at? You say at the, some people will say the data link at the physical layer, which I was saying that before, but technically it's really the MAC sublayer and the physical layer of the OSI model. Okay, so let me go back just briefly again. LLC is the one that takes the frame, the packet, places it into a frame, and stamps on the frame um, what kind of packet he put in that frame. That's all he does. He doesn't put any other addresses. The MAC sublayer takes that unfinished frame, puts the addresses on it, finishes it up, and places it onto wire. Think of it this way. The LLC is like the guy that works at a pizza place, and all he does is he makes the pizza boxes. The pizza box is the frame. The pizza itself is the data. So he takes the pizza, makes up the box, puts the pizza inside the box, closes the pizza, and then writes on top of the box what kind of pizza he put in there, right? That's what the LLC does. That's it. He doesn't write on it anything else or send it out. He doesn't know where it's going or where it's coming from. So he takes that pizza and then he gives it to the driver, the guy who's going to take it, the max up layer. The max up layer writes on the pizza box where it's coming from which pizza store, and where the destination is, and finishes a whole bunch of other labels he places on the pizza, and then he sends it out. That's what the media access sublayer does. And the media access sublayer, of course, it will be receiving pizzas as they come in, and he opens the box and gives it up when it needs to. All right, so that's a quick analogy of what the pizza. I'm not that hungry anyway, so I think I just thought of that analogy to make it a little bit easier to understand. Anyway, media access control. So your frame will travel in different media that traverses the network, with a dish to a satellite and so on. Your packet will leave a frame and get re-encapsulated into another frame as it traverses the network from one hop to another. Okay? So for example, I'll send out an Ethernet frame to the switch. The switch looks at the destination MAC address, and the switches do not open the frames at all. They leave the frame intact and they just send the frame to the router. It's the router that pulls the packet out of that frame and puts it into another frame so it can go outside. Okay? Here's a typical frame. Here's the packet. And when you add headers and trailers to the packet, this whole thing becomes a frame. Okay? And like I said earlier, the different types of frame, the format of the frame, and how it looks like, the standards are all being governed by the IEEE. So depending on what type of standard you're looking at, you go to the IEEE. 802.3.4.5, and you look up and they'll explain to you what the standard is and how it should look like, where the labels should be stamped on the frame, and so on. Okay, so controlling access to the media. But before we even go there, let me just make sure you understand. I got some notes here. Let's say I want to make sure you understand how data transfers. This is a typical question that I got on a CCNA test, and Cisco love to ask this question. Let's say, for example, let's say you have PC1 and PC2. PC1 is direct connected to router 1, and PC2 is connected to router 2. This is a NIC right here on this PC. This is a NIC on the router, NIC 2, and there's another NIC on the other side of router 1. This is NIC 4 on router 2, another NIC on this side, and another NIC for the PC. So these are NICs, Ethernet NICs. Let's assume, and let's say NIC 1, this NIC 1 has an IP address 1, for example, and a MAC address A. NIC 2 has number 2 and MAC address B. And NIC 3, number IP address 3, MAC address C, and so on. Okay? Let's assume that we want NIC 1, PC1 wants to send data to PC2. Okay? So let's say right here, after you finish creating, so let's say at NIC 1, would be this IP address. The source IP address will be this guy's IP address, which is IP address 1, right? What would be the destination IP address on the packet? Will be PC2 destination IP address, right? NIC 6, right? His IP address. So it'll be number 6, right? That's the source IP and that's the destination IP. What would be the source MAC address? Who's the sender? PC1. So it's MAC address A. What would be the destination MAC address? Where are you sending the frame to? Remember, the frame gets sent to another guy who's directly connected to you. It's NIC 2. NIC 2, it will be receiving that frame. So the destination MAC address is B. Now remember, what's inside that frame? It's the packet. And the packet has a source IP address that's coming from PC1 and going to the IP address that's for PC2. That's inside the frame, the packet. On the outside on the frame, who is the sender of the frame? PC1, which is NIC 1. And who is receiving that frame? It's going to be the router, right? So when the router receives that frame, he pulls the packet and he gives it to NIC 3. And NIC 3 now he's going to encapsulate that packet into another frame. So let's say we are now at NIC 3. When he pulls that packet out and puts it into another frame, NIC 3, what would be the source IP address? Still 1. It doesn't change. What's the destination IP address? It's still 6. The packet doesn't change. You just pulled the packet out and you are re-encapsulating it into another frame. Now, who is the sender? NIC 3. So he puts his MAC address on the frame. So that would be MAC address C. Who's the destination MAC address? Who's going to be the receiver of that frame? NIC 4. So you place NIC 4's MAC address, which is MAC address D as the destination, right? So now router 2 receives that frame, pulls the packet out, and gives it to NIC 5, right? Now let's say you are at NIC 5. What would be the source IP? The packet doesn't change, right? You just pull the packet and you are re-encapsulating it into another frame. Okay, now what would be the source MAC address at NIC 5? He's the sender. NIC 5 is the sender, right? So NIC 5 is E. What would be the destination? F, right? NIC 6 will be receiving that from. As you can see, as the frame Packets get re-encapsulated in different frames as they traverse the network. The packet itself doesn't change, but the frames, change it. They change. You are traveling in different frames as you are traversing the network. All right. If you have any questions on this is very important. You need to understand that remember that packets travel in different frames as they move from one hop to another. Okay, I'll promise you, uh, if you ever take the CCNA or CCENT test, they'll ask you this question because that's a fundamental that you need to know. All right. So question number, I don't know, 5 is it? Well, you know what? We'll leave that question. There's no question number 5. Don't worry about it. Let's continue here. All right. Going back to here. Now, controlling access to the media. When you want to send data, uh, you want to make sure that you don't collide. There's no traffic. No one else is using the media, the wires, in other words. This is like similar going onto a highway. As soon as you come into an entrance of a highway, you stop or you yield and you look for traffic. Okay, because you're sharing the media, you're sharing the highway. You want to make sure it's either you take turns. There's a standard on what you do so that you don't get into an accident, right? The same idea with sending out data. When one computer wants to send out data, there is rules that they need to follow because if they don't follow the rules, there will be a lot of collisions onto the media and no one will be able to transmit any of their data. All right, so sharing the media. By the way, that's why switches are preferable because everybody will have a connection to their destination. It's like you are connected to anywhere you want to go, and no one else will be on the road. You have roads for you immediately, no matter where you want to go. That's what switches do. They're collision-free environment. You have your own segment to anywhere you want to go. That's why it's preferable that you go with switches. Okay, physical topology. Physical topology means the way you physically connect all of these devices, all the devices in a LAN or a WAN together. All right, you know, one of your duties when you first get a job, and if you are responsible for a LAN or a WAN, is you need to know how all of these devices are physically connected to each other. Okay, so if you have a diagram, follow it, follow the cables. If you don't have, make sure you have a drawing out. You can use video or any way you need to have, any way you can, even if you have to draw it by hand. You should follow the wires and make sure you have a nice drawing of the physical topology of your LAN. You need to know how all of these devices are connected and what connected to what switch, to what router, what hub, right? So in case you need to expand or you need to troubleshoot, you already have it in there. So you could do that on your first day on the job. So, one of the first uncomfortable things when you get a new job is you don't know what to do on your first day. Well, there's something to do. You need to know how the physical topology and the logical topology, you know, what subnet each PC is located in, um, all the what are their IP addresses, so in case there's any troubleshooting, or maybe you need to add a device or take out a device. In fact, you can go into actually privileges and security, which group are you in, for example, and what kind of rights and privileges do you have for each group. Okay, so write down the logical topology, how they software-wise connect to each other, in other words. So you can spend a couple of days on your first day on the job learning the physical and the logical topology of your LAN, and then you'll feel a lot more comfortable. So in case you need to troubleshoot, maintain, upgrade, whatever you already have previous knowledge, you're eventually going to need to know it anyway. So might as well do it first day on the job when they don't expect a lot from you, right? All right. What are the common physical topologies out there for WAN and even LAN? There's point to point, two directly connected, well, virtual directly connected if we're talking about a WAN. A star topology, where everything goes to hub, or a mesh topology. And the idea between a mesh, you can, if one side goes down, you can always connection. There's always another way. But this is a little bit more expensive because every connection will cost you. All of these connections may not be used. So point to point, logical point to point. This is like when you're downloading it uploading data between two devices the same. It's as if they see each other on the same network, but they're using the internet to connect. So this is what the cloud is. The cloud means really you don't know where your data is flowing, and who cares as long as you get it. You know, all of these devices in the cloud, they look at the addresses on the packets or the frames, and they move your data till they get it to your destination. Okay, half duplex and full duplex. Half duplex means a device can only either send or receive data at a time. It doesn't do it at the same time. A switch will negotiate that with the device. The switch can either be full duplex or half duplex. If it's half duplex, if it's hey, are you half duplex? That means all right. When you're sending data, the switch will not send data. If the server is sending data to the switch, therefore the switch will not be able to send him data. He has to wait till he finishes sending the data. But a full duplex connection means the server will be able to send and receive data to the switch. And that's, of course, the preferable method. You got to get the NIC. The NIC has one port, by the way, and it uses the 8 wires in the unshielded twisted pair cable to send and receive at the same time. The NICs are a little bit more expensive. Most switches will support either a half or full duplex. They will negotiate that with the device. In other words, the switch will go and say, "Hey, are you half or full?" If the server says I'm full, then the switch will say, "All right, I'll be full too." If the server says half, then the switch will switch himself to a half duplex. For a LAN topology, the most common is either the star topology, where everything goes into one central location, like a central location such as, well, a concentrator, let's say, or switch or a hub, or those switches connect to each other and you have an extended star. The old Ethernet used to use a bus topology where all of your devices connected to cable, like the 10 base 2 and the 10 base 5 connection. The ring topology is typically used by a token ring network where all the devices have to be connected into a ring. They actually designed a device that interconnects those, such as the multi-access unit for token ring MAU, and the data will be sent to the ring. And what you do is if you grab a token and you have it, then you can transmit the data. Okay, question number 5. What are the 4 common physical topologies in a LAN environment? And there they are: star, extended star, bus, and ring topology. Okay, so contention-based topology means that first come, first serve. We'll discuss that next week when we talk about Ethernet. So that means it's like you go to the road, and if the road is free, get on. If you're lucky, you're the first one on, and you win, and you start transmitting data. That's called contention-based. You're trying to contend and fight to see if you can go first. That's how Ethernet works, by the way. Control-based means everybody gets a turn. Okay, you don't go and fight. It's not first come, first serve. If I give you a token, then you're allowed to go to transmit. If you don't have the token, then you cannot transmit. And that's what token passing is. The token ring does. You pass the token to the next guy next to you, and if he has the token, and if he wants to transmit, he can transmit as long as he has the token. And after, let's say, 5 seconds, then he has to release the token and give it to the guy next to him. That's control base. You can control who can and cannot transmit by either giving that device a token or not giving him the token. All right. Contention based, like I said earlier, is used by Ethernet, and they use the carrier sense multiple access with collision detection, or even the wireless uses also contention based, and they use the carrier sense multiple access, but with collision avoidance. All right. Again, we'll talk about for multi-access. For example, when this guy wants to transmit, what they do is they into the entrance of a highway. So what you do is you go in and you sense if there is traffic, and you wait if there's traffic, of course. If there's no traffic, you jump in and you try to transmit. So let's say A wants to transmit and D wants to transmit, and they're both waiting. So that's what carrier sense means. They're waiting on this road to see if there's traffic. And if there is traffic, they are waiting. Once the road clears up, then A and D jump in at the same time. That's what multiple access means. They are allowed to transmit if they sense that the segment is clear. But when they jump in, they know there's a very good chance that someone else jumped on with them. So they turn their collision detection on to detect if there's a collision or not. And if there is, they back off and they set up a timer. And whoever timer expires first is allowed to come back to the segment to sense if there is traffic. And usually one of these two guys his timer will expire first, and then there are he is the one that is allowed to come back to the segment. And when he comes back to the segment, he sees that the segment is cleared and he starts to transmit. But when D timer expires, goes back to the segment, sees that A is transmitting, so he waits. That's how really Ethernet works when it's connected to hubs. And this segment right here is called the collision domain, because that's where everybody would collide if they tried to transmit it at the same time. You don't want to be part of a big collision domain. That means there's a lot of PCs trying to share that same wire. You want to be on your own collision domain, your own lane to send to anyone. That's what a switch does. Eliminate collisions. You'll have your lane to transmit to whatever you want to. Now, control based is what Token Ring uses, or the FDDI, the Fiber Data Distributed Interface technology. And the way it works is if you put your devices in a ring, one guy in the ring will be called the active monitor. That active monitor will create a 24-bit packet called a token and passes it on to the guy next to him. If the guy next to him wants to transmit data, he'll grab the token, hold on to it for 7 seconds, and start sending out frames on the ring. And the frames will go in the ring, and everybody on the ring watches the frame to see if it's for them or not. If it's for you, by looking at the destination MAC address on the ring, you bring it in. If it's not you, you just ignore it. Now, after 7 seconds, even if you did not finish transmitting your data, you have to pass that token to the guy next to you, right? And then if you want to transmit, you grab the token. Now, by the way, if you have the token, you know there is nobody transmitting on the wire because you have the token. You are the one who's allowed to transmit. Therefore, the segment will always be clear. There will never be collisions, right? And then the token gets passed around. Now, if there's a lot of people on the ring, it's going to take a long time for somebody on the end before they receive the token if everybody wants to transmit. And by the way, once switches came around, that really killed the token ring idea because switches, you're going at full bandwidth all the time. Your throughput goes full bandwidth because you will always have a lane to your destination, and you don't even have to slow down and do carrier sense multiple access and detect if there's collisions. Because nobody will be on the road. When you send data to a switch, the switch looks at your destination, find out you're going, and think of it this way: it will create a lane to your destination, and you just keep going. You don't even have to stop to look for traffic. All right. So there is the active monitor, and they pass the token right around. Okay, so the frame itself, again, you can travel in different frames and you go from one device to another. So you need to make sure that your packet gets re-encapsulated in different frames. So sometimes the frames get lost on the way, get corrupted. So we got to make sure that you double check the frame, make sure it's okay. All right, before you accept it. So we'll talk about that in a few minutes. The, anything the header means, this is your data, this is your layer 3 package. Anything you put to the left, you stamp on the left of the packet is called the header of the frame. Anything that you stamp on the back of the packet is called the trailer. All right, then you put the MAC addresses on there. Where do you get your MAC addresses from on the frame? You get the source MAC address you get from, and the destination MAC address you get from an ARP request, for example, if you are in a LAN. Okay, so you'll have the destination MAC address, and when you send it to everybody, you broadcast to everybody if you are on a multi-access topology, and everybody will be examining the destination MAC address of that frame that's coming in, and you accept it if it's yours, and you drop it if it's not. All right, so anything on the back of the packet is called the trailer. And we'll talk about the FCS number as we move along in a few minutes. All right, so here we go again. Like we've discussed earlier, the packet travels in an 802.11 frame, is sent to the